Hello again, folks, possibly for the last time. Not to be dreary. Today I'm going to go over the solutions for the final exam, and then we're basically it then. Anyhow, if I need to, I may tear through my old notebook and try to dig up the diagram, but mostly what you need is just on the actual test itself. And it's all multiple choice, as you can see, except for the last question. I initially had it planned as being an extra credit, but it's not necessary. Anyhow, let's go through this. Let's see, it writes nicely today. It's decent, right? Good, okay. Let's see. For the chapter 2, let's see. First one is find the exact distance between these 2 points that are given. And then there's the distance formula. All right. The distance formula is the square root of 2x's subtracted and squared plus 2y's subtracted and also squared. And it really is just a question of, how well do you know the order of operations? How well can you substitute given values and just stick with it until the end? In this case, the coordinates that are given to you are 5, -3, and -2, 8, respectively. Let's make sure I duplicated it correctly. It looks like it's good. All right. Anyhow, what you should do, and I probably on the document I put it in a bracket just because the way that square root gets typed is that it doesn't have the little roof on it here. So that was really just to encapsulate everything underneath the square root or being affected by a square root. Anyhow, when you do these, you have to do the innermost parentheses first. And at this point, take a little artistic license, decide for yourself, right, which is the set of x1, y1, which is the set of x2, y2. My logic is that if this shows up in your face first, then this is x1 and this is y1, and therefore this is x2 and this is y2. It doesn't matter if you had the situation switched, right, it will work out either way, but just be consistent. The ones are together, the twos are together. And then put them in the appropriate places. So if I'm saying that x2 is -2, I'm going to squeak a -2 in here. Right, now bear in mind there's a negative in this formula. And then 5 is just regular 5. y2 is 8. There's a negative here. And then y1 is -3. So in that instance, you'll have a double negative. Right? If you go through the motions, right, a negative and a negative is a bigger negative. Same signs you actually add, and you produce a -7 squared. -7 squared would be a -7 times itself, which is just 49. Over here, a double negative is really plus, therefore this is 8 plus 3, and that is really 11 squared, and that is 121, which at this point you would appropriately add. And then you have the square root of their sum. Let's see, 0, 170. Now it just so happens that the square root of 170, although that is correct, the number 170 is not a perfect square. So if you were to take the square root of this, you'd have an irrational number. So even though intuitively you might go to your calculator, and there's no sin in that, but I would avoid it, right? Why? Because this, unless you could factor it into something that would be using smaller figures but expressing the same quantity, right? This is exact. So this is preferred as an answer, right? How do you know that you shouldn't go further than this? You try to factor it ideally into the highest perfect square that is possible, because if you do have a perfect square worked out as one of 2 factors, then that will leave the radical at least. In this case, what would you get stuck with? I want to say it's going to be 17, which is prime, and then the number 10, all right, which if you factored further would be square root of 2 and square root of 5. 10 is an example of a number that would be inconvenient to factor further, like the square root of 6 is another famous example. So although it's arguably a large quantity, you wouldn't bother doing it. You check, right? And then after a while, you just don't bother anymore because you go, okay, I got it. All right, I recognize that this one is problematic. Anyhow, this is what you should get for the answer, the square root of 170, and that's fine. If you wanted to estimate what this is as a decimal, just figure that it's between, let's see, 12 times 12 is 144, all right? And 13 times 13 is 169. So that's pretty close, right? 17 times 17 is, I want to say, 196. So this is like 16 point something. Rather, 17 times 17, I want to say is 196. Let me see. No, wow, that's way off. All right. 289. What's 17? Well, 14 times 14. That's what it is. Don't be, all right. Here, I'll write it. Which two perfect squares is this between? 169 and I believe 196 is the other one. Now, the square root of 169 is 13, and the square root of 169 is 13, and 196 is 14. So you would have to figure that this is probably, you know, about 13.5 if you had a guess. Right? It's an educated guess. So here is actually the square root, just to say good. Okay. Square root of 170. Yeah, 13. Oh, 13 and change. Okay. Yeah, this is closer to the 13, right? It's just one number higher. All right. So that's that. Moving on. Okay, the blues are going to be trouble today, I can see. Erase this. Save the space. Next one is 2. Find the equation of a line that passes through the given point and is perpendicular. Now, a couple of things. There are line relationships that would be good to know. There's, in general, there are lines that are perpendicular. Let me rephrase this. Lines that cross, right, would be more general. And lines that never cross, right? Of lines that cross, they just cross at any angle. And then there are those that cross at a perpendicular angle. So 90 degrees. And there are lines that never cross because they are parallel. Now, in terms of formulas, the feature that you could tell that two lines are going to cross just at any angle, non-specifically, is that they would have different slopes. If they cross specifically at a perpendicular angle, which is what you asked for, 90-degree angle, then they have opposite sine reciprocal slopes. That is, if it was positive in one instance, it would be negative in the other, and if it was negative in one instance, it would be positive in the other. But also, they're reciprocals. So one may be a fraction of a half, so then flipped upside down, it would be a reciprocal, would be 2. All right. If you were trying to make something parallel, they have the same slopes, and then as a technicality, right, they have to have different y-intercepts. All right, the b value. All right. Because if they have the same slopes, they might otherwise be riding alongside one another into infinity. All right. If you want them to be parallel, that they never cross, then you have to sort of separate them. They have to have a different y-intercept. Right. In the case of perpendicular lines, the intercept is really irrelevant. Right. It could have the same y-intercept or it could not. Right. What's more important is that they have opposite sign reciprocal slopes. So taking that into consideration, and noting what the formula was that was given, the equation of a line given from number 2 was this: y is equal to negative 2/5 x plus 3. And they're insisting that we use the point negative 2, 1. Pardon me, positive 2, 1, I'm inventing a problem. And is also perpendicular. Okay. The trick to this is to use the point slope formula. Which looks like this: y minus y sub 1 is equal to m times x minus x sub 1. It's a little faint, right? Green, you always have a pain in the neck. That might be a little bit better. Okay. And just like before, you really just have to decide for yourself, what is x1, what is y1. They gave you a point, so I would assume this is x1 and this is y1. And I can substitute those values pretty quickly. 1 would go here, and positive 2 would go here. It just happens to be a negative in the formula. Now, as for the slope, you would need the opposite reciprocal. So what is this? Opposite would be positive, reciprocal would be 5/2. As for the other x and y, you leave them alone because you need them to exist as part of your answer. There'll be another line equation that will just be the one that is going through this point and happens to be perpendicular to the original one. So, straighten it up a little bit. If you can't do anything on the inside of this parentheses, distribute. That means that you end up with y minus 1 is equal to 5/2x. And then when you multiply 5/2 times 2, we can make it over 1. The 2's cancel, and you're just left with minus 5. Scoot over this 1 by adding, and you have y equals 5/2x minus 4. This would be the equation. Because of the difficulty in writing a fraction, what I did, you'll see in the choices, is that I wrote it sort of sideways. And you have it be A. Okay. Next, 3. Solve the quadratic equation. I should just stick with one color, maybe. 3. We need to solve this quadratic is x squared minus 6x equals 13. Use the quadratic formula. The reason why you would use the quadratic formula, which is this, x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a, is because even if you try to arrange this, right, in the standard form, And you'll need to do that anyhow. It's not going to be factorable. Usually factoring is the go-to method when you're trying to solve a quadratic equation in tandem with the zero product rule. It isn't going to factor in this case. Incidentally, this is the standard form of a quadratic equation, which unfortunately looks similar to the general form of a quadratic function, all right? They use those two words not interchangeably. It's such a stupid, subtle thing, all right? But be careful of that. When you talk about equations rather than functions more specifically, this is standard form, right? If you had this instead, this would be called a general form of a quadratic function. Function rather than equation, because there's a standard incarnation, which is also known as the vertex form, not to go off on a tangent. Anyhow, if you rearrange this to solve, well, for the sake of producing that equals 0, you would subtract 13 and you would just plop it over here. And then you would have this, x squared minus 6x minus 13 equals 0. No matter what you try to do in terms of factoring, and usually it would be something to a binomial times a binomial, it's just not going to work. The x's would be x squared, right? But as far as 13 is concerned, it only has, it's a prime number, it only has two factors, 1 and 13. And if you add them, you get 14, not 6. And if you subtract them, you get 12, not 6. So you can't factor this. There's a word for that. A word for that is there's a word for that, which is prime. When a trinomial like this cannot factor, we call it prime. Anyhow, we still have the quadratic formula. We just have to identify what is sitting in the A position, what is sitting in the B position, and the C position respectively, and then insert them into the formula. So, not too complicated. The A value is 1, right? So I will squeak a 1 in here, and also here, all right? The B value is -6. So I'm going to put -6 in here and -6 in here. In the case of substituting for a negative, I would be extra anal retentive and wrap it in its own little parentheses, because if it has an exponent of 2, both of those are being affected by it. The digit and the sign. And then there's C, which is -13, the same thing. I'm going to squeak in a little negative here. Right. If you look at the square root, which you should do first, this will decide whether you have a real solution or potentially an imaginary solution, a complex solution. If you get a negative under the square root, which I don't think that happens in this case, no, thankfully, you'll end up with a complex solution. Anyhow, your focus should be here, the discriminant, if you wanted to be technical. All right. -6 squared is 36. A negative ultimately times a negative is a positive. That's why it ends up being real. 4 times 13 is 52, which is a terrible number, but so be it. 36 is 88. So you have the square root of 88 here, plus or minus, sitting on top of 2. And then there is a double negative here, is just regular 6. What you should do as before is factor the square root, because maybe, even though this is never going to be completely exposed, all right, the radical is never going to go away entirely, at least you can express the quantity in terms of a smaller figure, all right, or a pair of figures. So ideally, remember you want to factor into the highest perfect square possible, and then some leftover. A leftover is sometimes a prime number and sometimes a composite number like 6 that it just would be inconvenient to factor further because it wouldn't factor into anything that would help. Right. So in the case of 88, it's okay if you start with 8 times 11, right? But the highest perfect square would actually be 4 for 88, and that would be times 22, right? The square root of 4 at least would become just the number 2. So you would end up with a 2 out here, and then a 22 left behind on the inside. If you attempted to factor this further, you'd get stuck with 11 times 2, right? And neither of those is going to leave the radical, so it's more convenient to just leave it like 22. Now what you can do is simplify the guts that you have left over here. You could think of this, since they're sitting on the common denominator of 2, as being one fraction and then a second fraction if you like. All right. 6 divided by 2 is just 3, plus or minus. The 2's would cancel in the other case, and you'd just be left with 22. That's why this is your answer. And there are 2 answers because it's adding in one case and subtracting in another. All right, so 3 plus or minus the square root of 22. Okay. This factoring is also referred to as the product rule for radicals. But that's the strategy. Highest perfect square, ideally, and then whatever the leftover is. Sometimes prime, sometimes not. All right, next one. Some of these I stole from, well, many of these. The first, first 11 or so problems on this final exam I took from my test number 1, because I'm trying to cover the entire semester. So I took out what I considered the most important things from test number 1. Oh, blue. No matter which blue I use, it's always a pain in the neck. Out of the batch that I have, anyhow. So, avoid that. Is this one okay? It's all right. It's a little stubborn. It's actually pretty good. Alright. Here's 4. In this case, the suggested method, you didn't have to do it this way. I remember on the test number 1 that a lot of you were very creative and you actually got the right answer anyhow. So I was like, oh, that's cool. They went and did what was more intuitive. So good. Alright. In the case of 4, I had suggested, just because I knew of what would eventually follow it in terms of trigonometry, that if you had something like this, that what you might do, instead of the arduous task of, distributing here, you have the perfect square trinomial here, distributing -3, and then combining all the guts and then attempting to factor it later, all right? Maybe try U-Substitution. If you didn't do U-Substitution but you still got the right answer, then that's fine, all right? But be open to the possibility. Now, there are some criteria that you need to meet in order to justify U-Substitution. When is it appropriate? I would say U-Substitute when you have something that is a trinomial or trinomial-esque, you know, like a trinomial. It may not technically be, but it's three terms separated by pluses or minuses in descending order. Meaning that the exponent degrees go down. Number two, the exponents have the same bases. However complicated they may be. The first degree is double the second. And lastly, the third term is a constant. All right. Try U-substitution when these criteria are met. All right, all four. All right, now in this case, it would eventually work out to being something that is a trinomial potentially, right? Right now it has a lot more terms, but they may be combined. Trinomial. It's in descending order, all right? You notice that the degree diminishes out of existence, right? It would be degree 2 to technically degree 1 here, and then degree 0 technically, and then nothing, you know. The first degree is double the second, all right? And the third term here is a constant. Oh, and one thing I skipped here. The exponents have the same bases, right? They're ugly, it may be complicated. It could be a trigonometric function inside the parentheses, but they're the same bases. So in this case, you have an algebraic expression here and here, but they're the same thing. They're x plus 5. So the point of U-substitution is basically this. To not get distracted, you fill in the void with something that is just some other letter, U, right? And then go about the process of factoring unbothered, you know, for lack of a better expression. Not distracted by the fine details. Then later on, you reverse substitute, so to speak. If I just call the base x plus 5 u, then this would be u to the first. And therefore this would be u to the second. And this would be minus 4 equals 0. This is a little bit more normal. If they were just x's, you wouldn't bat an eyelash. You'd go, oh, yeah, I can do that in my sleep. Why? Because a trinomial, something that's 3 terms wide, usually factors into a binomial sitting next to a binomial. And if it's the letter squared here, then what is it on the inside of the first ones? A u and a u, an x and an x, what have you. If you consider the factors of 4, there's just 2 pairs, 1 and 4 and 2 and 2. Of those choices, these two, 1 and 4, potentially will make 3. So that would be the better choice. Right? And then you, as an afterthought, you consider what the signs are. If this is shrinking somehow, these numbers are shrinking to make this number here, then that means subtraction had to have occurred. The sign combination that causes subtraction is one of each, meaning one thing is negative and one thing is positive. If you want the outcome to be negative, the larger magnitude has to be negative. So you have that. Okay. Now, you could employ the zero product rule, or you could at this point sort of reverse the substitution. You have it factored, so you could take what u represents and then insert it here and here, and then straighten it out. It's not going to hurt it one way or the other. Let's say that in place of the u, I put what u represents, which is x plus 5. Now I could combine these and go about my business. 5 plus 1 is really plus 6. 5 minus 1, 5 minus 4 is x plus 1 is equal to 0. Right? Now I employ the zero product rule, which is to suggest that perhaps this chunk, this factor, since these two things are being multiplied, perhaps this thing by itself is equal to 0. Or perhaps this thing is equal to 0. And then it's a matter of solving a one-step equation. Minus 6, x is equal to negative 6 in this case, minus 1, x is equal to negative 1 in this case. Now, if you go through this much trouble to do something, you should check your solutions, all right? But if you stuck negative 6 in here, you'd get negative 1. Negative 1 squared would still be 1. If you stuck negative 6 in here, same thing, you'd get negative 1. But a negative 1 times a negative 3 would be a positive. Right? So then you have 1 plus 3 minus 4, and then indeed equals 0. Right? And in a similar way, if you tested negative 1, it should also work. Okay. Figure out which one of these is the pain in the neck. Alright. The next is techniques for solving rational equations. To solve a rational equation, what you might do is write an equivalent by canceling denominators. All right. How do you do that? You cancel denominators by using the LCD, and you multiply the LCD by each of the terms. The whole equation. So if you have this to start with, x sitting on top of 2 plus 1 is equal to looks like 4 over x. Let's figure out what the common denominator is. Ideally, it is the lowest common denominator, the least common denominator. Least common multiple, lowest common denominator, same difference. It doesn't have to be that, that's just the ideal situation, right? Something that would work. Now, here's the thing. If you multiply this entire thing by the lowest common denominator or any factor, as long as you do it to all terms and both sides of equals, you can get away with doing this. You're going to change drastically the appearance of the problem, but it's okay. It'll be an equivalent equation, all right? And that'll be easier to solve. So the common denominator here would just simply be these two things together. The denominator here, the denominator here, pressed together via multiplication, 2x. So, if I multiply across the board here, 2x times this, 2x times this, and 2x times this, in this instance, the 2 would cancel, and you'd be left with x and x, which is x squared. In this instance, it would be 1 times that, which would simply be 2x. And in this case, the x would cancel, and you'd be left with the 2. And 2 times 4 would be 8. And then you have something that is quadratic, it's degree 2. And you want to try pulling tricks here, so hopefully you can factor it. We're going to subtract 8, the 8's cancel. You're left with x squared plus 2x minus 8 equals 0. And now I will attempt to factor this. If it's x squared, it's probably x in the front of each of these. If it's an 8 back here, think of factors of 8, 1 and 8, or 2 and 4. Of those choices, 2 and 4 would be the better choice, because if you subtract, that would be 1 of each sign. 2 from 4, you'd get 2, the middle term. And if you multiply a negative times a positive, you get a negative 8, so this should be legit. The answer, applying zero product rule here, x minus 2 equals 0, would produce x is equal to positive 2. And in this case, x plus 4 is equal to 0, would produce x is equal to -4. Now you do have to look out for extraneous solutions. Extraneous solutions arise from multiplying or dividing by a letter, which you don't normally do, you just usually take the coefficients, or by squaring usually. So in this case, I did in fact multiply by a letter. What is an extraneous solution? It's a dud. Basically, it's an answer that although it's algebraically correct, if you went back to the original equation, not the manipulated version of this, but the original equation and tested the answers, it might give you some nonsensical contradictory answer like 2 equals -9 or something like that, rather than a letter equals a number. So you should test this 2 in here and test this -4 in the original equation, right? And they both actually work in this case. So these are correct. But just beware of that. There are also oftentimes extraneous solutions. X plus 2, x is -4. Okay, I'm losing my stuff. Is a bad blue. Causes me trouble. Try this one. 6 is solving a radical equation. When you have a radical equation, you have a couple of alternatives here. You could always employ, the most basic technique of solving something algebraically, which is to perform opposite operations, because opposite operations cancel. Or if you happen to have something that is in radical notation, you can convert it to rational notation. And in that case, you're going to take advantage of the power rule for radicals, exponents. The power rule for exponents was when you have an exponent raised to an exponent. In which case you multiply. But if you strategically multiply by the reciprocal, which is to perform opposite operations without thinking, there is similarly a cancellation effect. So in this case, if you had this given to you as x minus 1 to the 2/3 is equal to 9, all right? This is a radical equation. It's really this. It's really x minus 1, the cube root. The cube root of x minus 1, the whole quantity squared. Right? There's a couple of tricks you can pull here, but it's not going to help you in this case. Like if you wanted to, you could put the 2 on the outside. But anyhow, let me just go with it this way. If you wanted, again, to go this route, to produce some kind of a cancellation effect, you would just cube this, all right? And this would cancel this, and then you'd have x minus 1 squared. You just have to remember to then do it to the opposite side, in which case you get whatever 81 times 9 is, right? 729 or something. Something huge. In this case, what you might do is employ the power rule for exponents. When you have an exponent raised to an exponent, you multiply. Just strategically choose the reciprocal. So if this is 2/3, raise it to 3/2. And then do the same thing here. In that case, 2/3 times 3/2 would cancel out of existence. You'd just be left with x minus 1. This is a little bit more efficient, I would say. And then you have this, 9 to the 3/2. This is rational notation. Perhaps it would be practical to put it in radical notation. If it has a denominator of 2, it's a square root. And if there's a 9 here, it would technically have a 3. I'm going to tuck in the 2 as the index here. Right? It's not usually written, but just for the sake of clarity. Right? And then I could do what I was alluding to before. If it is a convenience for you, you could put this on the outside and reserve dealing with that last. So if you have the square root of 9, you could figure that out. Right? The square root of 9 would be plus or minus 3, but then it would be plus or minus 3 cubed. X minus 1. When you cube a negative, it maintains its negativeness, for lack of a better expression. So you're going to get one of two things. You're either going to get 27 positive, or you're going to get negative 27. So x minus 1 is equal to positive 27 and simultaneously negative 27. If you go through the motions now of rearranging this equation, add 1, add 1, add 1, cancels here. X in the first case would be plus 28, and in the second case would be negative 26. If you went through the process here, it would be a little bit more arduous just because you didn't cancel out the squaring here. So what you would end up with is this. X minus 1 squared is equal to whatever 3 cubed is. I want to say it's like 729 or something. 9 cubed, rather. Yeah, that's a huge number. 729, yuck. All right. It is not impossible to go this route. This is the perfect square trinomial, but it's going to be more trouble than it's worth. Use reciprocals, right? And the power rule is what it technically would be. When you raise an exponent to an exponent, is the power rule. All right. Also know how to convert between radical and rational notation. Notation is just a style of writing something. Much better blue. Okay. This one actually erases. Save that one. I got 5 blues. 4 of them are terrible. These 4. Look at these. 4 blue markers, and each one of them doesn't go away when you erase with it. Jeez. Alright. 7 is solving an absolute value inequality. And then answer in interval notation. So if you have this is 7. It's an absolute value inequality. And if it's an inequality, it just means that it's opting for one of these symbols instead of equals. If it's an absolute value, it has those lines. Now there's a couple of things to take into consideration. Based upon the orientation of these symbols, you will decide whether this is an and sort of problem or an or sort of problem. And the reason that you care is because one represents an intersection which changes the graph, all right, how it looks in the interval, versus the other type. So if you have it basically as the variable is on the left side of a symbol like this, and then you have some other number here. All right, this is an AND type of problem. I wrote that, good. If it's oriented like this, then it's AND. If it's oriented like this, then it's OR. Right? It happens to be, in the case that you were given, this. 2x plus 3 inside an absolute value is less than 5. Side note, the trick to this is to, if it's necessary, isolate the absolute value to one side. Right? In this case, it's already done for you, but if you had an extra term here, like plus 2, move it to the opposite side before you break up your into two problems. Okay. Now, because this is an absolute value problem simultaneously, it is possible that the thing under here is a negative, right? Or the amount that this works out to is a negative. So the way that we compensate for that possibility is that we write two inequalities. So you're going to duplicate all of these features. And probably the easiest thing to do is start by just rewriting the symbol as you see it oriented. And then in the other instance, flip it around backwards and make it negative. The outcome is negative. This again is taking into consideration that an absolute value could have a negative inside the modulus. So that's the symbol, the lines there. And we need to produce basically two sort of inequalities to get our spectrum of answers, the interval. Anyhow, the actual mechanics of solving it is not too complicated. It behaves just like an equation. So you would just move 3 by subtracting. In both cases, cancels. 2x would be greater than, in this case, a double negative is a bigger negative. Same signs, you add, you get a negative 8. Divide by 2, divide by 2. X would be greater than negative 4. If you're wondering about any sort of additional sort of flipping of the inequality symbol, that only happens when you are multiplying or dividing by a negative. In this case, I don't have one. There's no negative 2 here, right? If there just coincidentally happened to be a situation where there was a negative, yes, I would have to spin this around once again. Annoying as that is. Anyhow, this is one spectrum of answers, and now we will go for the other. 2x is less than, this is a positive 5, negative 3, one of each says that you subtract, and you end up with a 2. Divide by 2, x would be greater than 1, less than 1. Okay. This is the other spectrum, and these are AND. AND types of problems are intersections, which are sometimes represented by the horseshoe shape, all right? And intersection means that, as far as we're concerned, we're only interested in where the graphs overlap. We want them to overlap. If they don't overlap, that means that there's no solution, right? In the case of an intersection. So, next thing. Draw a picture. If they ask for the answer in interval notation is something that looks like this, right? It has a lower boundary, a comma, and an upper boundary. And the way that you signify that there is the lower boundary is included in solutions is that you put a bracket, right? And the way that you would signify that, say, for example, an upper boundary does not include as part of the spectrum would be just a curve, a parentheses. It kind of unfortunately looks like a coordinate, but it's not because it's one-dimensional actually, it's just x's, right? It's just a shame. I would nonetheless draw a picture, right, and keep it simple. Incorporate the numbers that are relevant here, negative 4 and positive 1. In relation to 0, negative 4 would be here. In relation to 0, positive 1 would be roughly here. It doesn't have to be perfect, but that would sort of be, estimated. Now, if you are strategic and you arrange your equations so that you have the variable on the left side of the symbol, it kind of tells you which direction the arrow goes. If you didn't do that, you could always compensate, but this is read as x is greater than -4. So where are the things that are greater than -4? That way. The real question is, though, is there an equals in this at all? There isn't. So in the old-fashioned way, you would circle this to say, that isn't included, it's just a reference point. It's not part of the answer, so to speak, but it's where I would start looking. And where are the things that are the answers? They're that way, into positive infinity. Simultaneously, when you graph this one, again, if you're strategic and you have the letter written here in relation to the sign, it kind of tells you which direction the arrow goes. Anyhow, there is no equals in this. So I would also include a circle here, a hole, if you will, just a reference. And I would say x is something less than 1, which you could reason through would be things running this way. Now again, because this is an and statement here, because of the original orientation of this inequality symbol, it is an intersection that we're interested in, meaning both criteria have to be met simultaneously to describe what the solutions are in common. And therefore, in terms of the graph, we only care about where the graphs overlap. So where do they overlap? They overlap in here, between these points, and not beyond them. If we were going to opt for the newfangled symbols to represent holes, right, what we would have instead is parentheses like this. Right? And this is the lower boundary and this is the upper boundary. So in terms of interval notation, we would write this. That's the interval. That's the spectrum of answers that are correct or make the original inequality true. Right? They exist in this stretch of the universe of numbers. Okay. Now we get into something that's a little less practical, a little bit more theoretical. Black is my favorite marker because it writes so well and it erases so well. It's perfect. All right. 8 is the question, determine whether the function, and then the function looks like, this is 8. The function of x, which is equal to -2 times the quantity x minus 1 squared plus 3. This, if you're curious, this is a function that is a square function or quadratic function, most closely resembling vertex, i.e. standard form. Remember, when it comes to functions, they use the word standard rather than general. General is this expanded. All right. Anyhow, determine whether the graph of this function, all right, is 1 to 1. Let me remind you of something. In the world of functions and math in general, there's this concept referred to as a relation. A relation is any set of x's and y's, in the style of a coordinate. Doesn't matter how they're arranged. More specifically, there are functions which have specifically no repeat x's, or recurring, you might say, to sound a little bit more eloquent. No recurring x's, no repeat x's, no repeat input values. You can have several of the same output y values, but you can't have a repeat x. Right? Then there's a slightly more specific type of function, which is called a one-to-one function. And in that case, the symmetry would be, these are truly one-to-one. Right? For every x, there is a unique y. Right? For every y, there is a unique x. Right? That means essentially that there are no repeat x's and no repeat y's either. If you were just given numbers to stare at on a piece of paper, the coordinates listed, then you could tell right away, just looking at the numbers, that it's 1 to 1. The reason that you care, right, is ultimately because 1-to-1 functions have inverses. And you've seen inverses, and you know how to create inverses. It's one of the questions on this test, right? But only this type of function can be produced as a, can make or have an inverse. That's really why you care. Now, as far as graphs are concerned, and I would plug this into my calculator, right, rather than go through any other technique. Functions simultaneously pass something called the vertical line test, right? 1-to-1 functions, because they're functions, also pass the vertical line test, and something called the horizontal line test. Now, if you entered this into your calculator, where it says y equals, and then you set the screen dimensions to be standard, it will draw you a parabola of some sort. This is basically what the picture would look like. You'd have a graph that looks something like this. It would be upside down because it's negative. If you're curious, the exponent of 2 would make this a little bit narrower than normal, right? And the vertex would be shifted over, right, and up, right? This is why they call it the vertex, because these are the coordinates, right? The x value is the counterintuitive. Right. Anyhow, it's an upside down parabola for all intents and purposes. If you just wanted to tell very quickly whether this is a 1-to-1 function, right, try the vertical line test and then try the horizontal line test. If it passes the horizontal line test, the vertical line test, that's as if you drew a vertical line through the graph, right? If there's only one point of intersection per imaginary vertical line, then it's a pass, right? They already labeled it a function anyway, so it's a good bet that it probably really is. But, all right, this has only one point of intersection. So this is a pass, all right, in terms of the vertical line test. So far, so good. If you tried the horizontal line test, then you would draw a horizontal line through your graph, right? In this case, notice what happens. You unfortunately have 2 points of intersection. You're only allowed to have one. Only 1 point of intersection allowed per horizontal line to pass the vertical line test. So this is a fail, all right? This fails the horizontal line test. If it fails the horizontal line test, it's not a 1-to-1 function. No, not. Right. It's just a function. It's not a 1-to-1 function. Okay. All right. 9 is a formula again. Find the average rate of change, i.e. the slope for this function. This is 9. Average rate of change essentially is slope, right, for curves. All right. Normally we have the slope formula for a straight line because the slope is continuously the same thing through the line. If you had a curve, right, the slope would be changing, right, and therefore we want an average to kind of figure out where it would be, what the slope would be, maybe at between 2 specified points. So this is the formula. Well, here's the given slope. 3 minus 2x, and this little botchable loop, you notice. And this is the interval, which is 0 and 2. And this is the formula. The function evaluated at 2 minus the function evaluated at 1 over 2 minus 1. Here we go. Okay. This would be a secant line if you wanted to be really technical. Slope for a straight line would be tangent, right? All right, anyhow, you see something in notation like this, subscripts of 2, that's just saying this is the first one, this is the second one. You're going to evaluate the function using 2. That is, you're going to plug 2 into this, see what you get, right? Then you're going to do the same exact thing. You're going to plug 0 into this, see what you get, and then combine them. So I'll do it twice here. If this is really 3 minus 2 times the quantity squared plus a quantity, and I stick x2, which we're going to call the number 2, here and here, then eventually subtract these. I would have to do it again with this. 3 minus 2 times the quantity squared plus the quantity. In this case, it would be 0 in these two places. Follow the order of operations. Meanwhile, this is all sitting above 2 minus 0. That's the whole thing written out. Let's see what you get. If you were to straighten out what is in red primarily here, you would deal with the exponents first. This would be 4, right? And it would be 2 times 4, which would be 8. And then it would be 3 minus 8 plus 2, essentially. The subtraction and addition are equally important, so you will do the work from left to right. 3 minus 8 is negative 5. Negative 5 plus 2 is negative 3. And then there's this minus. And if I straighten this out, this one's much easier, right? This term goes away, this is just 0. Same thing here, this entire thing, squaring 0 is 0 times 2 is 0. And this is minus left over from the formula, and then that is coincidentally a 3 here. If I were to simplify the bottom, it would just be 2. So you have negative 3 minus 3 over 2. If you straighten this out, a negative and a second negative is a bigger negative if you're attempting to add them, all right, rather than multiply. If you have the same signs, as in this case they're both negatives, you add them really to get the number. So it's 6, but it's a negative 6. And this is sitting over positive 2. This means that the slope is negative 3. All right, finding inverses, all right, is 10. There's a procedure for creating an inverse, and you can kind of swap like step 2 and step 3. It really doesn't matter, you get the same answer. But it might be more convenient to do it one way versus another. Here's what I mean. If you want to create an inverse function, first thing is you're going to start with something that probably is written in function notation. Just call this y. Right? Then what you're going to do is solve for x instead. And then 3, you're going to swap the x with y and the y with x. And then lastly, you're going to use function notation. So you're going to call whatever y you have, you're going to call it the inverse function and write it like that. A superscript of -1 is not an exponent, it's just a notation, it's a style of writing. So, as I was saying before, if you wanted to switch sort of steps here, you could switch these two around and you will get the same result. You just got to be careful. Alright, if this is what they give you to work with, the original function is 3x plus 2. And I'm just sticking with my procedure here. The first thing I'm going to do is just call this y instead, because it's easier, especially when you're switching between variables. Normally the function of x is what y is a y value, it's just sort of disguised. If I now rearrange this to isolate the x, I'm solving for the x instead. Right? Then it's a matter of basically moving 2 by subtraction. In this case it will be -2 is equal to 3x. And then dividing by 3. And I end up with this. X is equal to y minus 2 sitting on top of 3. Now at this point, I'm just going to basically write a y where there is an x here, and write an x where there is a y here. I'm going to switch them. So this will be called y instead, and this will be called x instead. And the last thing is to just go, well, to identify this as an inverse, I'll write it in function notation. And this would be it, x minus 2 over 3. If you were to graph these two, they didn't ask you to do this, but it's kind of an interesting thing. If you graphed the original function 3x plus 2, you will get a line. If you graph this, you will also get a line. But what will happen is that they will be symmetrical to one another about a diagonal. Y equals x. They'll be sort of the mirror image of one another. I'll do it really quickly. This is kind of interesting. I may have to clean up my calculator a little bit, but what I'm going to do in y equals, just to prove a point, is I'm going to enter 3x plus 2. If I were to graph it, you would see that you would get a diagonal line like it normally is. That's not to be confused with this dashed line here. That's more or less the mirror, if you will. Now, if I superimpose the inverse, you'll see an interesting thing. I'll put it in the intuitive, nice way, so that it has an obvious top and an obvious bottom. You don't have to do that, but I think it's fancy. Minus 2 over 3. This would be its inverse, x minus 2 over 3. I may have to adjust the screen settings, but let me show you what you get. If you hit graph, you see that there's a second one here. It's slightly distorted because of the nature of the screen. That's why there's this other function. If you've ever looked in more or less the automatic zoom, there's something that says z squared. That makes the picture of the math universe a little bit more like it's supposed to be, which is that everything is square grid rather than stretched rectangular grid, which is just really to compensate for the screen dimension. So if I hit, you'll see it ever so slightly. Here it is as you see it. If I hit zoom and then go for z square, option 5, you'll see it squeeze a little bit. There you go. This is the original function. This is its inverse. And if they are truly inverses, they basically are reflections over this imaginary 45-degree angles here. So just to sort of emphasize, I'm going to put in a third thing. I'll just make it this line, y equals x. And I'll hit graph, and you'll see that it's right through the origin. This is a mirror image of this. All inverses and their functions will basically behave like that. They're symmetrical about this imaginary diagonal line. It's kind of cool, right? The last thing is a question of how well you grasp transformations. Describe the effects of the changes, and you could use your calculator to help. All right, describe the effects of changes below to the standard absolute value function. All right, a couple of things. All right, an absolute value function is just no more complicated than this. Right, it's like saying, if you're opting for y is equal to the absolute value of x, and the effect is that you get a V shape like this. These points are interesting. It would be a perfect V, all right? And it would go through the point 1, 1, 0, 0, and negative 1, 1. And it would be oriented up like that. If, on the other hand, you have something like this, and yes, you can make your calculator graph absolute value. Negative 2 times the absolute value of x minus 1, I scribbled on my paper a little too much here, plus 3. This is emulating our transformation model. All right, I'm going to draw it just sort of underneath it. When we have a transformation model, it might look something like this under normal conditions. It might be a sine here, H, B, and K. Depending upon whether you're talking about the trigonometric incarnation of this or the one that is more quadratic. A couple of things to remember. The degree, all right, identifies the type of function. Like if it was a square, and it isn't, it's just absolute value, then it would be a parabola shape, all right, rather than a V shape. This doesn't have that. It has the actual operation is these absolute value modulus lines here, and that's why it's a V shape. So this is the operation, right? Absolute value. That's why I know it's a V shape. If you wanted to, let me just point at it. If you hit math, yeah, I'll show you. Press math and scroll over to num, ABS, and then the function, open-ended argument here, would allow you to draw absolute value. So for example, if I went to or you can go through alpha as well. If you hit alpha and then window for F2, you'll see that absolute value is also there. Anyhow, let me clear up these things. If you just wanted to do the absolute value of x for the sake of comparison, you'd have just that, right? And you'll notice that it makes a V shape, which is cool, right? If you typed in underneath it, I won't just expose it right away, what is given to you, it'll draw, and you can pretty much tell from the drawing, well, how is this different from the original thing? And then read the choices, but you can reason it through. Let me just humor me for a moment. Plus 3, okay. This is how it would look if you entered it. Notice that this is a negative, which means that I use this button rather than minus. It's just temperamental. Okay? Here's what I'm getting at, right? If you have a negative, as you do in this case, this means that it is a reflection. It means that it's flipped upside down. And then specifically, it's vertically reflected. Right? Flipped upside down is a more colloquial way of speaking. Right? So you would have that to begin with. You'd have an upside down being. Right? If you have a coefficient sitting in the A position, right? This is a vertical stretch. If it was a fraction instead, it would be a vertical compression, right? But a vertical stretch just basically means that it gets a little bit narrower like that. There is no b value here, it's just 1. That would be, if it existed, a horizontal stretch or compression. Since it's really just 1, and there is no change there, right? A horizontal stretch or compression is a similar effect, really, to the opposite vertical stretch or compression, right? Then there's this, the vertex. This is what you might call a horizontal shift. And it's counterintuitive. And this would be a vertical shift. And it is intuitive. Meaning what you see is what you get. The truth is, these two things in tandem are the vertex coordinates, if you just make sure that you compensate in the case of the horizontal. They sometimes call this h and this k instead. The vertex point, therefore, would be counterintuitive to 1 would be positive 1, and intuitive to 3 would be positive 3. That means that over 1 up 3 would be your V shape would be here instead. I should have done that in red if I had any sense. Make that a little bit more faint. So that's what you would expect the graph to look like. Anyhow, I'm going to show you now by having the calculator do it. Hit graph. And there's the other incarnation of this. It's a little bit, it's not too easy to see, but it's a little bit narrower. If I play around with the graph, it might be a little bit more obvious. Ever so slightly. Anyhow, you could tell from the picture what the effect is. The best choice out of the choices listed is that it is vertically reflected because of this negative, that it is vertically stretched because of this 2, and that it is shifted 1 to the right and up 3, which is choice B. We're out of the first test territory, and now we're into the more recent stuff since the quarantine. All right, let me see if I can speed myself up here a little bit. Number 12 is, given the quadratic function, convert to standard vertex form. Here's 12, right? It's given f of x is equal to x squared plus 2x minus 3. Here again is that unfortunate discrepancy between functions and equations. What we have here is the general form for a quadratic function as opposed to an equation. And what they want us to do is to convert this to standard form of a quadratic function, right? Which is also known as vertex form because it tells you where the point is, right, for a parabola, right? In that case, you want it to look more like this. The h and the k representing the horizontal and the vertical shift, technically speaking, in the context of transformations, but that's the vertex right there. That's why it's convenient to have it in this form. There's 2 different ways you can do this at least. One way is much more complicated, and that is utilizing the completing the square method. All right? What would be easier is just to simply convince yourself of this, that you could use formulas. The vertex, which is normally an x and a y value, is just going to be called an h and a k. Right? The h standing in place of x can be calculated from this formula, b over 2a, and then the k standing in place of y is equal to the function evaluated at h, or x, whatever you like. So if this is in general form, then just pluck out what is A, what is B, not C in this case. There is in fact a second formula for the Y, K, whatever you want to call it, incarnation of this, but it's just easier once you've calculated X to insert it in the function and then evaluate it as such. It will tell you what the Y is. Anyhow, A is 1 and B is 2. So if you put a 2 in here and a 1 in here, what do you get? -2 over +2, which means that h is equal to -1, right? So you will go here and you will insert -1 into the formula, okay? Right, which means that this will reduce at least to x plus 1 by itself. That much is done, all right? You could very easily steal what the a value is up in the front. It's just 1, which you don't really have to write, but you could if you want to be very thorough. And then there's the matter of figuring out what the y is, right? Which again is to evaluate the function using this number. So if you put -1 in here, right, then it would be -1 squared plus 2 times -1 minus 8. This is 1, this is -2 minus 8. 1 minus 2 is -1. -1 minus 8 is -9. That's the function evaluated at h, essentially, which is another way of saying x. So therefore, that is what y is. That is what k is. So you would put -9 here. To write it most cleanly, this is the standard form of the function. X plus 1 squared minus 9. See where we're at in terms of time. An hour and a half in. Oh boy. This is going to be a long video. Long. Alright. The numerator of a rational function reveals the x-intercepts, alright, of the function. Using the function below, factor the top only, and then try the zero product rule. So, if you had this for 13, man, that writes nicely. And we're looking for the x-intercepts, all right, for this function. X plus that x squared minus 2x minus 3. We really only have to pay attention to the numerator, just the top, all right? The reason is that when you're looking for an x-intercept naturally, what is true of the y value of an x-intercept? It would be 0. What represents 0? The function. So if this whole thing is equal to 0, whatever I've done with the bottom here, to move it around, it's going to cancel out of existence because it would be 0 times whatever this gobbledygook is. And the bottom line is you'd still have 0 here. This is what's left over. So to sort of circumvent having to go through that exercise, you could just pay attention to the numerator. And in which case, you solved this, you didn't even have to factor it, it was basically done. You'd get this, x is equal to -4. Right, if you wrote that in the style of a coordinate, the coordinate would be -4, 0. It has one x-intercept apparently, this function. You can make your calculator draw, and then you can see that that is true. It only touches the x-axis in one place. Okay. Now for 14, same exact problem. You sort of shift your focus. In the case of 14, geez, if I just learned how to write. What are you looking for? Vertical asymptotes. Remember, vertical asymptotes are a boundary where the graph will not penetrate. If they're vertical, their x equals some number. Right, in this case, using the same function, now factor the bottom only. These are the reason why you only have to pay attention to the denominator in an instance like this is because there's a domain restriction. Remember what domain is, what x's are allowed to be. If you have a rational equation, as you have in this case, the domain is not allowed to, the denominator is not allowed to be what number, or else you go to math hell, 0. That is a domain restriction. And a domain restriction in the context of this function is a vertical asymptote. So you really only have to pay attention to the denominator in this case. And since it happens to be x squared minus 2x minus 3, and you just kind of pretend for right now that you're factoring it like you normally do. And instead of just calling it equals 0, so you employ the 0 product rule, you're just going to remind yourself, well, it can't equal that. All right. X and x for x squared, 3 and 1 for the 3, minus and positive to produce a -2 and a -3 when you multiply. A -3 and a +1 when you add. X plus 1 is not equal to 0. X minus 3 is not equal to 0. If you went through the motions here and here, you would subtract 1. You get x is not allowed to be -1. That's a vertical asymptote at that location. If this was a graph, at the location of x equals -1, you'd have a dashed line. Over here, add 3, x is not allowed to be equal to +3. At the location of 1, 2, 3, +3, there would be similarly a dashed line. Your graph would be somewhere in here, and here, and here, but not going through those vertical asymptotes. Okay. Next question. Oh, good, I was consistent. All right, 15 is the same function. Rational functions are interesting among other reasons because they also have horizontal asymptotes, imaginary horizontal dashed lines, if you will. All right, and indeed are sometimes even slanted. All right. Basically, there are 3 rules for determining these asymptotes. I wrote them here. All right. Rule 1, Rule 2, and Rule 3. Rule 3 is when you have a diagonal. All right. Rule 1 is if you examine the degrees, and I'll make space over here now. Hopefully that's not too faint. Good. This is a function. If you examine the degree of the lead coefficient of the top and the bottom, all right, then compare it to rule 1, 2, or 3 that's written on the paper here. All right. Right. If the top degree is less than the bottom degree by 1, right, then your horizontal asymptote is pretty much in the normal place. Right? It's the x-axis, otherwise known as y equals 0. if the top degree is equal to the bottom degree. And what you would have to do in that case is basically consider what the coefficients are and then divide them. Right, so whatever number is here, whatever number is here, divide them, and that would be y equals something. You would divide top coefficient by the bottom coefficient. And then the outcome of that would be y equals something, as opposed to y equals 0. In this case, what you have, well, in this case it's actually situation 1, it looks like. Let's see. Just for the sake of comparison, if you had this alternative, if you had the top degree being greater than the bottom degree, then the graph is there's a slanted asymptote. And in that case, you'd have to use polynomial division to estimate. Right? You'll get something that you'll call y equals, right? And since it's a slanted line, it will basically emulate y equals mx plus b. It just might have a remainder on the end of it, right? And the remainder you'll just ignore, right? Because you're estimating. Right? Anyhow, which of these does it most closely resemble? Well, if you have a 1 here and you have a 2 here, then 1 is less than 2. Therefore, there's a horizontal asymptote along the x-axis. So as far as this picture is evolving, at -1, there's a vertical asymptote. At +3, there is a vertical asymptote. And then, in theory, though it will be hard to see, along y equals 0, the x-axis is a horizontal asymptote. So again, your graph would basically be bounded in one of these 6 places, or perhaps several of them. And you can use your calculator to draw that. Okay. I didn't write it, I should have. Okay. I'm making my key, I got ahead of myself here. To distinguish this problem from the next one, I changed the function finally. Perhaps I should have erased that, but oh well. Okay. In this case, you have use polynomial long division or synthetic division to approximate the slant asymptote. This is if situation 3 were to arise. And if you're given something that looks like this, x squared plus 3x minus 3 over x minus 1. Again, considering those 3 rules, the degree here is 2, the degree here is 1. So therefore the top is greater than the bottom degree by 1, right? So we're going to use polynomial division of some sort. You could try long division, which works 100% of the time, or you can get away with synthetic division in this case. All right, I'll try to do it both ways just for the sake of argument. Polynomial long division would be to take the dividend, which would be the top here, and place it inside a division box like so. And I'll draw the work here. And then systematically divide the first by the first. X squared divided by x would leave you with just x. Put that in the quotient. Then you're going to subtract 2 things simultaneously. You arrive at what that is by taking the quotient you just got and multiplying it by x minus 1. And you get x squared minus x. And then the reason I'm putting this parentheses here is because you have to remember you're subtracting two things simultaneously, so this negative gets distributed. And first terms cancel, a negative and a negative becomes a positive. This is 3 plus 1 really, which is plus 4x. And you drag down negative 3 and you repeat the process. The first term divided by the first term. The x's cancel, you're left with 4, which means that this is plus 4. Right? We still have to subtract two things. So we're going to arrive at what those two things are by taking the quotient and multiplying it by the divisor, x minus 1, distributing, and you get 4x minus 4. And you're putting this parentheses here to make sure you distribute the negative when time comes. Okay. The 4x's cancel, a negative and a negative is a positive. This will leave you with a plus 1. Since you're out of terms to carry down, this is the remainder. In terms of the function, which I'll just call it y is equal to x plus 4 remainder 1. If you wanted to be fancy, you could say that this is y is equal to x plus 1 plus the remainder is 1 over what you divided by, which is x minus 1. Now, as far as getting the slant is concerned, you're rounding it, essentially. I'm going to use a squiggle equals here. I'm going to call this x plus 1, basically. You could type this into your calculator and it would be fine. Right? But that's basically where the diagonal line would be. 4, rather, sorry. Jumping the gun here. 4, 4. There you go. If you did this via synthetic division, there's some criteria that you have to meet. Right? The divisor has to be linear, at least if you don't want to get in trouble. It is possible that maybe you could force this to work, but I don't think I'd like to do that. The divisor is x minus 1, right? It's degree 1, so it is in fact linear, so far so good. All right? The coefficient of x has to also be equal to 1, right? If it's not written, you would assume that the coefficient of x is 1, so check, both are fine. Then the last thing is that you're going to change this constant, c, to its opposite sign, right? To make sure that the arithmetic works out. And then you fit it into a table that looks something like this. That opposite sign of positive 1 I'm going to put here. The coefficients of the original dividend are 1, 3, and 3. I will put them here with their signs. And just the coefficients, the letters you're purposely ignoring. Right? I'm going to make sure that this is where it should end, so I'm just going to draw a little dash line here. That's where the remainder would sit if there is a remainder. Right. Then you drag this down, plus 1, and you multiply instead. 1 times 1 is 1, I'm going to put it here. Do the arithmetic, this is 4, do it again. 1 times 4 is 4, put plus 4 here. Subtract these, you end up with a plus 1. And then you write the outcome, the quotient, 1 degree lower. Okay. So if this was x squared, this is x to the first, right? This would technically be x to the 0, which you won't write. And then this is the remainder of positive 1 over x minus 1. Whatever you divide by, that's its denominator. Okay. Shouldn't have to waste $10,000. All right. 17 is given the log. All right. The log of x base 1/7 equals 2. Convert this from logarithmic form to exponential form. All right. And in that case, it's really just drawing that jelly bean that I often allude to. All right. Here's what I mean. That kind of looks like a jelly bean to me. All right. This is the base as it would be in the model. And this is its exponent, 2. And then you read it sort of counterclockwise. It's equal to x, in this case, because that's what's the argument. If you were to square this, right, the numerator and the denominator would both be affected, therefore x would be 1/49. Okay. If you have a situation like 18, and again you're going to solve an exponential equation that is base e, 10a minus 8 minus 5 equals -41. Couple of tricks. When you have base e, right, you'll use its inverse, which is the natural log. Right? There'll be a cancellation effect. And it's sort of like doing opposite operations. Anyhow, before you do that, isolate base e. So in other words, move 5. Right? By adding 5, and then you have this. That's a just complicated exponent here. This is -41 plus 5 is going to be -36. All right, you could move the 9. Is it to your advantage to do that? Yeah, I would. Okay. If it's pressed against this, you're going to divide here and here. You're left with e to this complicated exponent is equal to a negative over a negative is a positive. 36 divided by 9 is just 4. Okay, now at this point, use your inverse property. If you were to take the natural log of this, all right, that's like taking the log of base e to this. E to the 10a minus 8. And just make sure that you do it to both sides. So natural log of 4 would be over here. The natural, when you have the same bases as you would in this case, the effect is that this reduces to the amount of 1, right? At the same time, you might say that, well, the power rule for logarithms would say that if you have an exponent here, that you could just write it on the side here, all right? Usually people kind of jump the gun and they just go right to it, and there's nothing wrong with that, but this is the intricate justification. Natural log of e is the same base, so therefore they cancel to 1. And then because of the power rule, really, 10a minus 8 would be on the same tier now, no longer an exponent. If it's times 1, none of this is changing. It's just 10a minus 8 is equal to the natural log of 4. Move 8 by adding 10a is equal to the natural log of 4 plus 8 divided by 10. This would be the outcome. Natural log of 4 plus 8 sitting on top of 10. Next one is using your powers to simplify and then to solve logarithmic properties. If you have the log of 4x squared minus 10 plus the log of 3 is equal to the log of 51. I'll give you a hint here. Use properties of logarithms, right? And I put the product rule and the one-to-one property underneath it, so you use, okay, I know at some point I have to utilize that. Now, as long as these bases are the same, the bases here and here are the same, then you could condense this, all right, according to the product rule. And the product rule would say, all right, I could just write this as one log, and incidentally would be base 10 if you wanted to write it, but it's understood. You could now combine these. 3 times 4x squared minus 10 is equal to, on the opposite side, is the log of 51. If you've gotten it down to this point, that you have one solitary logarithm here, set equal to one solitary logarithm written here. And again, these have the same bases. This was the product rule that I took advantage of to condense these two. And now what I'm going to utilize is the one-to-one property, which says that whatever the guts are here, the argument here, if these are one log is set equal to a log, you could rewrite it as just the arguments. So you really have this. And I would clean it up, all right? Do the distributing, right? So this is 12x squared minus 30 is equal to 51. Move the 51 over to here to condense it. Leave a 0 behind. This would be 12x squared. 30 and 51 would be 81. And then attempt to factor it. Let's see. I could move it the other way, that's true. Maybe I'll do that. There's probably more than one way to do this. Perhaps it would have been better if I moved 30 instead. 30s would cancel. And then I would have this. I'd have positive 81 here. Then divide by 12 over 12. And now I have this. X squared is equal to 81 over 12. We could employ square root property because it's quadratic. I was thinking of maybe factoring it. You probably could do it that way, but maybe this is less work. Or just think about it as opposite operations. If I want to square root this side, it will expose just x. And then I would have to do the same thing to the opposite side here. According to the quotient rule for radicals, if it is a convenience for me to do so, this opposite side can be broken up into two pieces. The square root of 81 sitting on top of the square root of 12, and deal with them separately. The advantage to doing that here is that at least 81 will escape the radical as just 9. This down here, the square root of 12 is not a perfect square root, perfect square, so it's going to be irrational. What I'll do is I'll factor it according to the product rule of radicals, right? And ideally break it into 4 times 3, because at least 4 will escape the radical as 2. Which means that this is now 2 over the square root of 3. That is technically simplified, but you can go one step further, which is to rationalize the denominator. That is to basically make sure that the denominator doesn't appear in the denominator. The radical square root of 3 does not stay there. It doesn't appear in the denominator. So in that event, here's what you might do. When you want to rationalize the denominator, that basically means that you're going to multiply by a convenient ratio of the amount of 1. what is equivalent to 1, because multiplying anything times 1 will not change its value. It might change its appearance if you do it so strategically. What that usually means is what is the radical here is going to be duplicated as the radical over itself. Square root of 3 is 1.7 something forever, but that ugly thing divided by itself is still 1. Top times top is 9 over the square root of 3. 2 square root of 3 times 3 is 2 times the square root of 3 squared, technically. Which means that this would cancel this, and it would be 9 square root of 3 over 2 times 3, which would be 9 over the square root of 3 over 6, and then you can simplify 9 and 6, right? Divisible both by 3 because they both bend at the factor 3. This would become 3, this would become 2. 3 square root of 3 over 2 would be the answer. And it technically would be plus or minus, right? I forget to do that a lot. So it has a square root. Okay. Okay. Now we're in the trig territory here. Let's see. Find the angle between 0 and 360 degrees, right? That is coterminal with 375. All right. Now remember, coterminal angles have the same, known as terminal side. What does that look like? Well, here's a picture. Let's just say hypothetically that this was, I'm going to make sure that this is not the same exact problem, but 45 degrees. Right? This side, if this is 0, this is the initial side. This is the terminal side. The side where you actually read the angle if you had a protractor. Coterminal angles have the same terminal side, so even if you rotated through so many extra degrees and got a larger number than 45, the number that would be in the same place, essentially, would be coterminal to that. In theory, you could keep rotating through a complete rotation, 360 degrees, and keep getting infinite coterminal sides. That's really what you must do, right? When the angle theta is greater than 360, right? Keep subtracting. Right? That is the angle minus 360, right? Until within the confines predetermined. In this case, the question is asking a coterminal angle between 360 and 0. Okay. The other situation that might arise is when your theta value given to your angle is less than 360 degrees, keep adding. All right, so it'd be 0, pardon me, theta plus 360. That's a theta. Okay. So this is the given angle, again, minus, this is the given angle, again, plus. Now, what they give us? They gave us this. Given is 375 degrees. We're basically trying to figure out what regular range of numbers does this coincide with? 375. Well, let's decide. Is it the angle given bigger than 360, or is the angle given less than 360? I would say it is this situation. 375 is greater than 360. So therefore, what I'm going to do is I'm going to subtract 360 to see where it would land in the usual situation. Unfortunately, my stupid computer here is trying to update. I have to tell it not to. Sorry for the distraction. I was a little worried it might kill my video in the middle of it. Alright, so I'm going to subtract 375 minus 360, which is again one rotation. It's 15 degrees. So if going through 360 degrees from 0 lands me back here, going through 360 degrees from where I left off at 15 would get me to 375. Right, it's one extra loop. So that's what it is. It's 15 degrees. It's coterminal to 375 degrees. Are we on time at the 2-hour mark? I think I could finish this in under an hour, hopefully. The only reason it really matters is that it just takes so long to upload. It isn't a linear relationship either. I don't want to say that if it's more exponential, if anything. If it's 1 hour, it's 3, you know? Okay, 21. Find the exact value for the sine of 240 degrees, right? The exact value is a ratio, right? So like square root 2, something like that, you know? And I added this little diagram to sort of help it along, right? What the purpose of this exercise is to get you to sort of memorize, right, these points, right, on a coordinate plane. 0 degrees, which we'll read counterclockwise, 90 degrees, 180, 270, and this 360 would be in the same place. If they're telling you, find the exact value of 240, right? Which quadrant, 1, 2, 3, or 4, would 240 most likely be in? Right, based upon these numbers here. Well, starting from 0, that would be 90 degrees, another 90 would be 180, and if I went all the way here to the y-axis again, I would be at 270, but that's overshooting it. So therefore, one would have to figure that 240 is probably somewhere in quadrant 3. And the reason ultimately that a person cares, right, is because if you were to draw an imaginary right triangle, and it would always be perpendicular, incidentally, to the x-axis, right, that would cause this to be a negative y component, and this would be, coincidentally, a negative x component. This is the x-axis. So you have basically a triangle that looks like this. Negative y, negative x. Okay. Now, in a similar situation as to before, if you wanted to figure, well, if I have to get exact ratios here, which might have square root of 3, square root of 2 in it somehow, and I want to decide, is it the 30, 60, 90 situation, or is it the 45, 45, 90 situation, we need to figure out what this correlates to, right? Which special right triangle relationship is this most similar to? All right, so what I would suggest is this. If you're in quadrant 2, all right, then similar to before, subtracting, adding, you're going to subtract the angle from 180. If you're in quadrant 3, as we are in this case, then you're going to take the angle and subtract by 180. Okay. If you're in quadrant 4, then use 360 instead. Okay. If you're in quadrant 1, you really don't have to worry about it because it's more or less the normal situation. So, what are we after? We are in quadrant 3, so I'm going to be doing this. I'm going to take 240 and I'm going to subtract 180 to figure out how far down this way relative to the x-axis I am. So 240 minus 180 is how much? Let's see, 20, it's 60, right? So this would be a 60-degree angle in here. And therefore, though this is not drawn very nicely, this would be a 30-degree angle and this would be a 90. That means that this most closely resembles this special right triangle relationship, which is normally oriented like this. Make that a little bit more obvious, 60. And the reason you would care is because along the edge of the 30 is the dimension square root of 3. That's the x. And along the dimension of 60 is 1, and what would be across from the box, which would be the hypotenuse, would be 2. So this is, again, sort of botch of a loop here. So notice that we're going to have to compensate for a couple of things. Number one, if you're in the third dimension, this is a negative y and this is a negative x, whereas in the normal picture, we don't have to worry about that. Look at the edge that is along the 30, right? That means that y in this case is the square root of 3, right? And x in this case is 1, right? And this hypotenuse would be 2. Another thing to note, x's and y's can be negative, right? Right. R is always positive for all intents and purposes, right? That's helpful if you're trying to decide a trig relationship, right? It's only the x's or the y's that are allowed to be negative or positive. Okay. Now, moving on. All right. So, they want us to figure out the sine of 240 degrees, which we have decided translates to basically the sine of 60, right, in quadrant 3. Now, what is sine? Use SOHCAHTOA if you prefer. Sine of an angle is the opposite over the hypotenuse. Right? In the context of a coordinate plane, x's and y's, right, it usually translates to a y over an r. Okay, just remember, we have to compensate. There are negatives involved here. So, sine of 60 degrees is the dimension that is y, which is opposite of 60 here, right? Which is negative square root of 3, right? Over the hypotenuse, which is the r value, and again the r value is always positive, which is 2. So we have this exact relationship. The sine of 240 is equal to negative square root of 3 over 2. And that may not seem like much, but the truth of the matter is, because it involves an irrational number, square root of 3, remember, is 1.7, whatever it is. this is a better answer than just having the calculator give you some decimal, because even the calculator, in theory, if you were going to involve this as part of some other dimension, some other calculation, you'd have to chop off infinity at some point. Whereas if you left the ratio, right, you're preserving all of infinity. Right? So fractions, even though people don't like them, are really better than decimals when you're doing a calculation oftentimes. Right. So here's proof in the pudding. If you took the square root of 3 and divided by 2, I just entered it very simply like that, right? That's what I'm saying sine of 240 is, right? You get negative 8.66, whatever it is, into infinity, right? If you took the sine of 240, right, you get the exact same amount, right? Okay, it's hard to figure out what the ratio would be without going through the work. You can memorize something, but it might be more trouble than it's worth. Better to understand the basic intricacies of this. That's sort of an oxymoron, the intricacies of it, never mind them being basic, right? Okay. Moving on. Oh, this one's quick. 22, 23, and 24. All right. It says use the given function and the model of transformation. Okay, I put this here. Here's the given function, and here's the model. You notice that in the case of trigonometric functions, they just opt for capital letters a lot instead of lowercase letters. It doesn't matter. Here's what you usually have. A sine of the guts here, bx minus c plus d. These have all the same jobs, right? Really, they just might translate them ever so slightly, tweak them so that they conform to a sinusoidal waveform, all right? Instead of calling this a vertical stretch, which is what it really is, we call it an amplitude, which is the height of the wave. Instead of calling this a horizontal stretch, or compression, whatever you like, right? We call it the phase shift. Oh, pardon me, the angular frequency. Basically the speed, right? A type of speed, if you will. Angular frequency in a physics book is symbolized by omega instead of capital B. This is the horizontal shift under normal circumstances, right? But we're going to call it instead phase shift, which is scooting it in the sort of the lateral left or right direction as horizontal shift would, all right? But it's not deforming the shape of the wave necessarily, all right? Just moving it over out of phase, all right? And then there's D, which would be the vertical shift, but instead we're calling it the midline, which is what the wave rides along. They are basically the same jobs, right? In the case of phase shift, let me just specify one other thing. The C value does depend, because of the continuous nature of waves, depend on B also. So like for example, if you want to get the phase shift, you really should divide by B. It's just that B might be 1, in which case it's really just C. All right. angular frequency, although this is getting messy. The angular frequency, otherwise known as omega, B is the same thing, different textbook, all right, is this formula. It's dependent upon the period. This is something known as the period. Normally, a wave completes in the amount of 2 pi. If instead it's something else, this ratio will change that. All right? These things are interchangeable. If you rearrange this formula, you could calculate the period from the value of B. They're inversely proportional. And just remember, the period is the amount of, basically it's time, but it's the amount of pi units it takes to complete one wave. It's what we might think of as time. Okay. Anyhow, that's overkill, all right? But I wanted to just sort of, if I can help, elucidate, make it less nebulous, all right? Compare, I'm gonna write the model just above this, all right? A sine bx minus c plus d. And as you can see, there are some features included and others that are not. All right. What is included? There's an amplitude. All right. The b value would technically be 1. That would be the coefficient of x. There's no c included, so you would assume it is 0. There's no extra plus anything here, so the midline would be 0. Right? And knowing that, all right, and what they basically represent, amplitude being the height of the wave, all right, the vertical stretch, all right. If there is a decimal number here, something smaller than the amount of 1, normally 1 isn't written, right? Math people leave that out a lot of times. But if it's smaller than 1, what you would expect is that the amplitude is half as large, right? In this case, because it's 0.5. It's something smaller than it would normally be in terms of how tall it is. So this basically causes it to be shorter than normal. If this b value is just a 1 here, that means that it's just more or less normal, right? There's no distortion, right? The speed is not increased or decreased. The angular frequency is just basically a normal situation, right? If you wanted to calculate the period given 1, it's the usual situation. So a couple of things. Since a is equal to 0.5, that means that it's shorter, right? Since b is equal to 1, that means that the period is the normal period, the normal 2 pi. That's how long it takes to complete one wave, 2 pi. The c value, since c is equal to 0, all right, there is no phase shift. And since d is equal to 0, the midline, there's no vertical shift as well. All right, the midline is normal. All right, y equals 0, otherwise known as the x-axis. Right, these are things that you can tell from comparing this to the model. So what does it ask you? All right, what is the amplitude of the given function? For 22, it's 0.5, all right, so which is d. That means that it's vertically compressed. It means it's shorter than normal. That's choice D for 22. 23, what is the period of the function? Again, if you stuck a b of 1 in place of this formula here, that's the period formula. 2 pi over the absolute value of b, you just get 2 pi anyway, which means it doesn't distort it at all. It's unaffected. It's normal, basically. 2 pi, so the choice for 23 is C. All right, the period is 2 pi, the function completes one wave in the usual 2 pi frame. All right, what is the midline? The midline is 0. All right, so that means that the function is not vertically shifted. The midline is the x-axis. That's choice A. So 22 is D, 23 is C, and 24 is A. Okay. Now for 25, the next page, it says, is the given function horizontally shifted? The horizontal shift, otherwise known as the phase shift, is C. C depends upon B as well. Since it's over 1, then no, all right? If you put in a 0 here, this is dependent upon B as well. And you stick a 1 in place of B, and you put a 0 in place. There's no extra term here, right? A 0 here, then this is just 0, right? There is no phase shift. There's no horizontal shift. All right, so that's choice A for 25. Okay. Then as far as the picture is concerned, which of the following graphs most closely resembles the given function? You could use your calculator if you want to, right? But don't be intimidated either, right? Stare at the 4 choices, right? If the easiest thing is the amplitude, right? If the amplitude is normally 1, right? But instead, in this case, it's 0.5, and you know it's going to be shorter. Look at the choices that the maximum of the wave is 0.5. All right, that is choice C. All right, that is the option that you see here. This picture most closely resembles it. Notice that also the increments here, if you were curious, all right, the wave completes in the amount of 2 pi. The period. Alright, 27. Given the triangle below, find the angle theta to 3 decimal places. Right, so you're gonna basically rig your calculator to give you the correct ratio, and then you're gonna use inverse functions. So in the case of 27, you have a drawing that looks like this. This is read as being theta, and then the dimension over here is 12, gross from it, and then the dimension this way is 19. All right. And I suggested, this is a right triangle, SOHCAHTOA, which sounds like some terrible curse to somebody. Hey you, SOHCAHTOA. All right. Can, yeah, right. Ka. The initials of opposite over hypotenuse, the adjacent over hypotenuse, the opposite over adjacent. This is sine, cosine, and tangent, respectively. All right, if we are going to calculate the angle measurement, we need to basically rig this to be one of these. All right, I'm going to write them out. The sine of the angle is equal to the opposite over the hypotenuse, to be more explicit. The cosine of the angle is equal to the adjacent over the hypotenuse. All right, and the tangent in theory is the opposite over the adjacent, right? Based upon dimensions in the drawing, and you might be able to finagle something else. I mean, if you wanted to, you could use the Pythagorean Theorem, but based upon these dimensions, in respect of this angle here, this is opposite of it. This is adjacent to it. Which of these trig functions would be the most appropriate? Probably tangent, right? Because it has an opposite and an adjacent dimension. So opposite of theta would be 12, right? Adjacent to theta would be 19. And they want the angle. So if we have this ratio of 12 over 19, there is one thing that we have to do, use an inverse, right? Theta, this argument here, can be calculated from the inverse of this trig ratio. So you would essentially enter inverse tangent, which is second, and then tangent button on your calculator, over 12 over 19, of 12 over 19. So inverse, right? To get inverse, you hit second, and then you hit tangent. Notice in blue it says inverse. 12 divided by 19, and we're going to round it. You get 32, it's in degree mode as well. 32.275. 3 decimal places. Okay, I put it in, they wanted radians. Okay, radians. Sorry. All right. Let me change my mode. You could calculate it, but man, whatever. I'm going to go down here and change my calculator mode to radians. I'll go back up here, highlight that. I can spare myself from having to type it twice. And now we have that. 0.563. Theta is about, well, it's 0.5633. If they want it to 3 decimal places, that's as far as that 3. It's about equal to 0.563 radians. This is not pi radians, this is full-blown radians, which means that the calculator used 3.14, to convert it to a pure decimal. Okay, 28. Clean that. 28 says, given the inverse cosine of negative square root of 3 over 2, solve in the interval of 0 to pi, right, in pi radians. You have to do this by hand, at least part of it. Okay. A couple of things. I put some hints here. When you see an inverse function, just remember that inverse functions, we just did a problem like this, only it was tangent. Right? What do they give you? Right? They ask, what is the angle? They give you essentially the angle. So that means that if this was originally cosine, it would be the cosine of theta is equal to negative square root of 3 over 2. This is more or less undoing the inverse function and writing it more or less the normal way. Now, simultaneously, what does cosine represent? Cosine in general is an adjacent value over hypotenuse, right? Typically, that means x, but do be careful because it depends on, certain criteria. We're trying to fit this into the interval of 0 degrees to pi, which is also known as 180 degrees. So if we have a negative top, that means that we have a negative x, where in the coordinate plane are the negative x's. This is negative x, right? In either quadrant 2 or quadrant 3, technically, would be where the negative x's reside, right? But they're limiting us to just 180 as being the maximum. So we're not going to consider quadrant 3. Okay. If this is x over r, then imagine this situation where you have a negative x, and it would technically have a positive y in quadrant 2, and then there would be an r value here. This would be negative square root of 3. because that's what actually is sitting in the position of x. The hypotenuse would be equal to 2. And remember, hypotenuses are always positive, technically. All right? And then you could infer what the y value is if you really wanted to. I don't believe you have to. We're basically just looking for the angle. All right? And we're doing it by hand. Now, remember, the angle is read in relation to the x-axis. So if you were in quadrant 2, what are we going to do? We're going to take 180 and subtract to figure out the angle. That is the angle we're reading it this way. I'm going back from 180 to get the terminal side here. And we're going to translate it into what the angle would be this way. Now, if this has the dimensions, famously, of the square root of 3 and 2, then this is going to be a 1. And that means that this would have to be a 30-degree angle, because that's along the edge of the square root of 3. The edge of 30. This would have to be 60, and that's why it's 1, and this is the 90-degree angle. So we're going to backtrack 30 degrees, and we're going to get 150 degrees. That's what the angle should be. And that's what this question is asking, if you see an inverse, in a very subtle way. Right? Let's see if your calculator can produce that. Now, we also, even though this is correct, the criteria of the question is that, the requirement is that it wants it in pi radians. Okay. So, let me remind you of something. You can convert between types of units, right, based upon what is given to you. You're going to multiply by the appropriate conversion factor, which I'm writing in the style of a ratio because it looks like a fraction, and that will give you what you want. That's basically the plan. If what we are given at this point is 150 degrees, then in place of given, I'm going to write 150 degrees. I'll just make it look like a fraction by sticking a 100. If I want to convert this to so many pi radians, which is to have the symbol rather than multiply by 3.14, which would be a decimal purely, then what I'm going to do is choose the conversion factor. There's two choices, pi over 180 and 180 over pi here, that will cause a cancellation of degree unit. It would be pi over 180 would be the appropriate one, because if I want to cancel out degrees, and I'm kind of exaggerating the degree symbol, putting 180 down here would cause this effect. Then it's a matter of, you could simplify first if you want to, or just do brute force top times top, in which case you get 150 pi, and sitting on top of 180, then pull tricks. Crossing out pairs of zeros is like dividing by 10 without thinking about it. You might recognize a relationship of 15 to 18 if you have your multiplication tables memorized. Divide by 3 and divide by 3. The result is this: 5 pi over 3 radians is equal to 150 degrees. Our calculator, the TI-8384, doesn't give you this, right? It might give you the angle, but you'd have to be able to convert. So here, let's go through the motions. If we went to the original problem and it hit the inverse cosine of negative square root of 3, sitting on top of 2, close parentheses, that is if I have it typed like this, entered, all right? This will give me, as long as it's in degree mode, and I'm going to change it now, (150), the appropriate angle, all right? Because it's a negative square root of 3, and that has to be the top only, not the denominator, which is the hypotenuse. give me the appropriate angle. Then I convert it to pi radians. Yeah, Dodo, one mistake here. 180 divided by 3 is not 3, it's 6. Stonado. 5 pi over 6. 5 pi, sorry. Divide each by 3. Okay. $30. 29, sorry. I'm boring myself now. Boo! Hiss. How long we're at 2:30. Okay. This is gonna be a 3-hour video. Okay. Moving on. For 29, find the sine of the inverse cosine of 3 over 5. It would be written in that arrangement, right? Now, remember, you got to talk yourself through some things, right? If you see an inverse trigonometric function, don't be scared at all right? Just go to yourself, what is this going to give me? It's an angle, all right? Inverses give you angles. So what we're really asking here is, what is the sine of theta? What is that equal to? We have some dimensions given to us, since this relates back to a triangle, a right triangle. Draw a triangle. If cosine of theta is equal to the opposite over the, the adjacent over the hypotenuse. I didn't do that before, right? Because I hope I didn't. I really don't be if I did. And this is an X, and this is an R. Alright. Let's just put theta here. This is an X, and this is an R, and this would be a Y, respectively. If they're giving us the dimensions of 3 over 5, then that's 3 in place of X and 5 in place of R. There's a 3 here and a 5 here. We could use the Pythagorean Theorem, right, to figure out this third dimension, because this is presumably a right triangle. So, let's do that. We'll figure out what the y dimension is, and then we can answer sine, because sine would be opposite over hypotenuse. And that realistically is going to be y over r. We already know that r is 5. We just need to know y to answer this question. So, if the Pythagorean theorem is usually a squared plus b squared equals c squared, we're just translating it into, instead of a and b, that's an a, I swear, and c, y, x, and r, and it'll produce the same results. Right? Just put the appropriate numbers where they ought to be. In place of b, I've chosen that to be the x. B is in bottom, right? This will be y squared as itself, and then we'll put a 5 here. This is really y squared plus 9 equals 25. If I rearrange it, then y would equal the square root of 25 minus 9, which is 16. And that is 4. In the case of Pythagorean theorem, we don't take into consideration negative because we're talking about something that's measured. So this is a 4, right? That means that what is sine? It's 4/5. And if you enter this in your calculator, you get 0.8, which is 4/5. All right, 5 to go. the case of 30, you notice along the bottom, I give you a hint here. I said simplify the expression below using trigonometric identities, which is something that you would have as a table, unless you have it memorized. We're going to simplify this. If it is cosine of the negative x input times the sine, that's sine, I swear, of x, times the cotangent of x, plus the sine squared of x. Let's see what we could do with that. All right. The trick to this usually is trying to convert to cosine and sine exclusively. Okay. I gotta remind myself of a couple of things here. Cosine with a negative input, I forget if it's to say that it is an even function or an odd function. So I'll just pull this out to remind it. And myself as well. Here we go. Okay. Let me refer to this. All right. Cosine with a negative input is just the same as its cosine of a regular input. All right. These are even functions. All right. Which means that they're symmetrical about an axis forgetting I'm giving pi. Let me just show you this on Julius. Bear with me. I'm getting so weird. I'm obsessing a little bit right now, but it shouldn't be because I'm tired. I want my paper. Okay. I think it's a Lowell's clause. Anyhow, it's an even function, and the effect of an even function is that it is symmetrical in a certain context. So you could write a negative input x as just simply cosine of x. What you would see is that if it were reflected, I forget if it's over the y-axis exclusively, the horizontal axis, that is to reflect vertically, or about the origin. Odd functions, I want to say, are both. Anyhow, sine is already sine. Cotangent is the reciprocal of tangent. And tangent is the ratio of sine and cosine. So if tangent is really sine over cosine, then cotangent is that upside down. It's cosine over sine. Meanwhile, there's this free floating plus sine squared of x. Since these things are all pressed together, I'm trying to exaggerate the fact that they are being multiplied, so I'm putting dots. And then you could simplify things that are in respect of one another, one below the line, one above the line. These are like factors, they will cancel. That means that you have cosine times cosine, which is abbreviated as cosine squared. And if you combined it with sine squared. This is the Pythagorean identity. The answer is 1. That's kind of fun, right? Okay. My blood sugar as well. Let's see. All right. If you were going to solve a trigonometric equation, you were solving for the angle, but it's part of an equation that you need to manipulate algebraically, perhaps. Here's what we have for 31. All right. If you have 2 cosine squared of theta plus the cosine of theta minus 1 equals 0. I would once again attempt to translate this into something that is less transcendental. Transcendental things are trigonometric functions. They're non-algebraic, all right, because they're periodic. Translate this into something that looks algebraic. And the way that you do that is U-Substitution. All right, remember, we want something to be polynomial-esque, right, in descending order. All right, 2. That the bases of the exponent are the same. 3, that the first degree is double the second, and that the third term is a constant. And if that's the case, and it is, it seems to be it's not technically a polynomial because it's not even algebra. But it is in descending order. Right? It goes from 2 to 1 to nothing, 0. The third term is a constant. If you consider these to be the bases of the exponents, right, they're the same, cosine and cosine. What's different is that the first degree is double the second degree, which is not even written. So what we can do is just call this 2u squared plus u minus 1 equals 0. It's less distracting is the whole point. And then we go through the process of factoring this, because if it is a polynomial, that is a trinomial, set equal to 0 already, maybe it will factor, maybe I could use the 0 product rule, and then I could reverse substitute at some point. If you attempt to factor something like this, right, it's a little bit more complicated than just going straight to some binomial plus or minus some binomial. Being that the numbers are small, you could probably do that, but I'm going to do it more strategically. What I'm going to do is I'm going to use AC product pairs. Of factors and help me go along. If it's just 2 times 1 is just 2 is the product, and since it's just 2, then the only pairs of factors it has is 1 and 2. That means that what I'm going to do for the sake of factoring is fill in the missing number here. Break this up into a sum or a difference. I'm going to write this adjacent over here, 2u squared, and this adjacent minus 1 still equal to 0 over here, and then use the 2 and the 1 that are the only pairs of factors I have. I'm going to change this to a 2u and a 1u, and if you notice they shrink, they go from 2 to 1, which means subtraction had to have occurred. That means that one of each sign is necessary. If I want the outcome to be positive, then it's the 2 that has to be positive, and this would be minus. The advantage to doing AC product pairs is to establish how many different combinations of pairs of factors you have to work with. In this case, it's just 2. Then you factor by grouping, which is to just sort of pay attention to 2 things at once, just the front 2, and then eventually these 2 things, independent. It's easy to do 2 things rather than 3 things at once. The way that this would factor is 2u times u plus 1. And the way that this would factor, I'm just going to start with negative 1 here, would be u plus 1. Distribute, and you get the original thing here. When you get the situation where this matches this, the way it factors is like so. The match gets written one time, and the things that are the left outs, they get written one time. That's the factor. Now what you could do is you could reverse the substitution. What does u represent? It represents just regular ordinary cosine. So you can, at this point now that it's completely factored, squeeze cosine of theta in here. All right, and then solve these equations. This one is a tricky one because you have to draw pictures next. That's getting through the factoring. Let me show you what follows. If this is the cosine of theta plus 1 is potentially equal to 0. And then in the second instance, it's 2 cosine of theta minus 1 is equal to 0. The way that this would simplify, the way that this would solve would be to subtract, cancel, and then you have the cosine of theta is equal to negative 1. Okay. In this instance, moving add 1 cancels. 2 cosine of theta is equal to 1, divide by 2. In this instance, you get an actual ratio, 1 over 2. There's a couple of things that can help you along, right? Now, we've done all the hard part, really. All right, I should read the instructions to you. Solve this, find all the exact solutions. Now, exact implies that you're going to get some kind of a ratio. Right, you may have a square root of 2, square root of 3 in it. All right, and do that in the interval. Solve exactly all solutions in the interval of 0 to 2 pi, which is more or less a complete circle. Right? That means eventually we're going to have to look for solutions in quadrant 1, quadrant 2, 3, and possibly 4. All right, maybe 2 at a time, maybe all 4 of them. We'll see. Let me erase this was any of the space. Let me remind you of a couple of things. All right. If you have the graphs of sine wave and cosine memorized, you don't need your calculator to tell you certain things. You might just know. All right, here's a, you don't have to do this, but I just want to remind you of something. If you had a cosine wave, this would be pi over 2, pi, 3 pi over 2, and 2 pi, the complete cycle. The cosine starts at positive 1. At 90 degrees, it's here. At pi, it's negative 1. At 3 pi, it would be here. And at 2 pi, it's back where it started at positive 1. Anyhow, this kind of would help. If you happen to know this, it would only help you when you're trying to decide what's going on here. If you're trying to figure out what this angle is, you could take the inverse of cosine and it would tell you. And there's no sin in that. But if you know the picture of cosine, and this is the way it would look, at the location of pi, which is 180 degrees, all right, exactly at that location, that's what cosine of theta equals, negative 1. If this is a y value, all right, I don't want to go there. I'm trying to think, how shall I phrase that? This is, if the input is pi, then this is what the output is, negative 1. -1, notice, is just a number. It's not even a ratio. You could, if you wanted to, translate this into a fraction. How so? How could you make a whole number look like a fraction? You would have to put it over 1 to preserve the digit of 1. And you'd have to make it +1 as the denominator if you want to make sure that it's not violating some idea that only the x's, the top, right, would be a negative. What that is implying in a very subtle way is exactly what this is implying in a very subtle way. If this is 0, and this is pi over 2, it's 90 degrees, and this is 180, which is actual pi, and this is 3 pi over 2, 270, and this is 2 pi, the complete circuit. These are both alluding to the same thing, that the radius, and I'll sort of draw on top of it, the bottom is the radius, right? And cosine is normally x on top. The x dimension and the radius dimension are the same thing. In order for them to be the same thing, they're no longer a triangle. Basically, the x dimension and the radius are overlapping one another, which means that this is not in a quadrant. It's just lying along the axis here. This is -x, which just coincidentally happens to be equal to r, because if it's -1, that means that, in terms of its magnitude at least, right, the magnitudes would be the same. Okay, so that means that our solutions are neither in quadrant 2 or 3 for this, all right, half of it. It's right on the axis, right? What angle is that? All right. If the whole point of this exercise is to solve for theta, all right, remember the inverse of cosine would tell you what the theta is. It's 180, right? It's pi, right? Because this is 180 degrees. This is one of several exact solutions for theta. Pi is one of the answers. Now you could, if you wanted to, you could cheat. If you look at the solutions, there's only one of them and it says pi is an option. It's A. But as for the other ones, they come from this. Right? Cosine of theta, again, you could plug this in. The inverse of cosine times 1/2. Right? And it will tell you what theta is. The problem with the calculator is that it's only going to give you one. Of the two possible answers. How come is there two? Because if you're saying that this is the interval of 2 pi, and if this is an x over an r dimension, and the whole thing is positive, that means that we're dealing with positive x's. Where are the positive x's? The positive x's are in quadrant 1 and in quadrant 4. Which means that, and since it's not a whole number as an answer here, you get an actual ratio, you have an actual legitimate triangle. So we have a triangle oriented like this that produces positive x's. And in theory, a triangle like this, which is still producing or utilizing positive x's. What's different about these? This would be a positive y, this would be a negative y. This is the fourth quadrant. This would be r, and this would be r. We have sort of like a, I don't know if you're familiar with Star Trek, right? But it looks like the Klingon or the Romulan bird of prey, all right? If you look at these two triangles in tandem with this red line here. Anyhow, so fill in these dimensions. Dimension of 2 for the r's, dimension of 1 for the x's. Right? Then we'll go back and consider possibly which special right triangles we may incorporate here. So far we have one answer. From this, we know that theta is equal to pi. Right? Because that -1, that would have to be, the input would have to be pi. Right? We're looking at it that way. In which case the x value and the r value would have to be the same number, 1, in order to be -1. In this case, right, we have dimensions of 2 and 1. And if that's the case, if you have these special right triangles memorized, then the only other dimension would be square root of 3. Just remember that that would cause the angle here to be 30, because it would be along the edge of square root of 3, and that would cause this to be 60 instead, based upon that orientation. If basically we have a second triangle underneath it, like this, right? They're sharing that edge that's 1, you know? But this would be negative square root of 3, and this would be still 2. And therefore, the dimensions in here would be 60 again, and this would technically be 30, although we don't care about that. And now we could figure it out. Right? First of all, we're solving for theta, which again, you could do the inverse of the cosine of 1/2, and it would probably give you 60 if you have it in degree mode. It won't tell you the other one, unfortunately. So let me do this first one. We know that this has to be 60 because of the orientation of the dimensions. So therefore, if this is 60 degrees, in terms of pi radians, it would be pi over 3. All right, you can convert from what is given, 60, use the conversion factor of pi over 180, and it reduced to 60 over 180, which is the same as 6 over 18, which is 1 over 3, pi over 3. So we have pi and we have pi over 3. To get, that's just going this far though. If you wanted to go all the way this far, all right, you could do pull the trick. If you know that you're in 4th quadrant here, all right, you're going to take 360 and minus the angle. So that's really 360 minus 60, which means that this is really 300. This line is coterminal to 300. So theta 1, 2, 3 is 300 degrees. That one is a little bit more tricky. If you're going to convert it to pi radians, all right, let's just do it. 300 times pi over 180 is equal to so many pi radians. The degrees would cancel, top times top, bottom times bottom. You'd have 300 times pi over 180, cross out pairs of zeros. The relationship between 30 and 18 is that they're both divisible by 6. That's the GCF. This would be a 5 pi, this would be a 3. This is 5 pi over 3. Those are your 3 possible solutions, pi, pi over 3, and 5 pi over 3. For this original problem in that interval, which is choice A. A lot of work to that one. That was the hard one. And 32. All right, 32 is find the exact value of cosine of pi over 12. Cosine of pi over 12, right? Pi over 12 is not part of any special right triangle relationship, right? If you were to convert this, to so many degrees. This is a side note. Pi over 2 times 180 over pi would be, that's 12 rather. 180 over 12, divide by 6, divided by 6 is 30 over 2. This is equal to 15 degrees. All right, which is not one of our special right triangle relationships. We either have the 30, 60, 90 triangle, or we have, you know, the 45, 45, 90 triangle. So that stinks, because then we can't really do this by hand unless we change this somehow. What we'll do is we'll convert this to a sum of difference formula. It is hard, but try to conceive of either a sum or a difference that equals the amount of so many 12ths. Again, think of this without the pi symbol for a moment. Think of it as so many 12ths, right? And if it helps, you know, just focus on the 12 in particular. What equals so many 12ths if you maybe add, if I'm suggesting in this case, difference formula, right? What minus what would equal 1/12? If you want it to be a positive, and it is, then the larger quantity has to be on this side of the subtraction symbol. Right, so this will be positive so many 12ths. In order to add or subtract fractions, do remember they have to have a common denominator. And if you want the value to be 1, as that's what really pi over 12 is, right? What minus what equals 1? There's lots of things, right? It could be 6 and 5, right? We want something that potentially relates back to one of our special right triangles. So if it helps, you know, let's compile a list of things. Right. 30 degrees, and you have a table, you could, one of those handouts I gave you that correlates these, but 30 degrees is really pi over 6. Okay. 60 degrees is really pi over 3. 90 degrees is really pi over 2. Let's see, I'll put this in red here. 45 is really pi over 4, and 90 is itself again. All right. So there are these 4 things to work with. Right. Can you convert any of these to so many 12s? You can convert pretty much all of them to 12s, it looks like, because they're all divisible. But let's see. The way it's going to work out, it's kind of hard without trial and error, is that this is going to be 4 12ths, and this is going to be 3 12ths to make the 1/12 that is really pi over 12. All right. What does that reduce to though? That's 1/3, which means that it's really pi over 3. Same thing here. All right. What is this really? 3 over 12 is really 1/4, right? Which means that this is really pi over 4. So that's really what we're working with here. This is pi over 3 minus pi over 4. It's a little counterintuitive. As I said, the larger quantity has to be on the right side to make this a positive overall. But when you have fractions, it's the smaller number in the denominator represents a larger quantity. 1/3 is really 0.3, 3 repeating, and 1/4 is really 0.25, so it's shy of that. So if you subtract them, you end up with a positive. Right? Now, having established these two things, when we use the difference formula for cosine, this is as it looks. The cosine of alpha minus beta, which is what these two things are in the formula, is equal to, I have it written on the paper, cosine of alpha, cosine of beta, plus, I'm running out of space, sine of alpha times the sine of beta. We are going to input, in place of alpha, pi over 3 is what we have established, and in place of beta, pi over 4. So this is pi over 3, this is pi over 3, this is pi over 4, and this is pi over 4. And that really is the same thing as saying the cosine of 60 times the cosine of 45 plus the sine of 60 times the sine of 45. Okay, now each one of these things can then be translated into a trigonometric ratio. Right, I erased it, but do remember this one at least. I'll put them here and here. Oh, green, stop being so lousy. In the 30, 60, 90 triangle, this is normally the orientation of the 30. Right? Along this edge is the square root of 3. And if this is 60, then along this edge is 1 and this is 2. The cosine of 60 is the adjacent over the hypotenuse. But what's adjacent to 60 in this case? It's a y value technically, because of the way that it arranged it. Right? The way that I drew this triangle is the reason. But anyhow, the adjacent figure is 1. Right? So this means that this is 1/2. That represents this first trig ratio. Cosine of 45, it doesn't really matter in this case because the dimensions are the same here and here. But this is square root of 2. Cosine is adjacent to either one of the 45s. Well, that would just be 1 over the square root of 2 for the time being. So you have this times this. And then you're going to add sine of 60 is the opposite of 60 in this orientation, is the square root of 3 over the hypotenuse of 2. And then because I've got myself tucked into a corner here, now, sine of 45 is, in either orientation, is 1 over the square root of 2. There's going to be some rationalizing here. In order to combine all of these fractions together, we would have to have a common denominator. And we can't just multiply 2 times the square root of 2, even though it might be tempting, because that's a radical. That isn't. This rationalized, I'll put up here. If I remember, rationalize the denominator, 1 over the square root of 2 is multiplying by square root of 2 over square root of 2. The reason being I'm replicating this here and here is that this is really a ratio of 1, so it's not changing the value overall, but it induces a cancellation effect. This would be the square root of 2 squared, and this would just be square root of 2 on top. The effect is that it's square root of 2 over 2. So that's what would be here. 2, square root of 2 over 2 is the rationalized incarnation of this. And essentially the same thing would happen here. You'd end up with square root of 2 sitting on top of 2. You could test it with your calculator. If you divide 1 by square root of 2, you will get the same value as the square root of 2 divided by 2. Here's the square root of 2 divided by 2, 0.7. Here's 1 divided by the square root of 2, which is normally bad etiquette, 0.7. It's just rationalized. It's because it's a kind of a holdover from the days when we didn't have calculators. Makes it easier to not have an irrational number in the denominator. Anyhow, let's straighten this out. This is multiplication. So this is the square root of 2 over 2 times 2 is 4. This is the square root of 3 times the square root of 2. Legally speaking, they're the same index, so I could recombine them. They're the same index, so I can multiply. So square root of 3 times square root of 2 is square root of 6. Over 2 times 2 is 4. As far as fractions are concerned, I could legally add or subtract fractions, in this case it's adding, denominators, fractions with denominators that match. So the simplified answer is this. 4 just written once, on top is the square root of 2 plus the square root of 6. This is what the value of this would be. Okay, here's proof of that. If you took the cosine of pi divided by 12, you'd get 0.999999. Okay. Assuming that this is in the correct mode, I think I'm gonna have to change it. Let's see if you get square root of 2. No, do that first. Square root of 2 plus square root of 4 divided by 4. Yeah, if there's a discrepancy, that means that I need to change the calculator's mode. It's in degree mode right now. I need to change that to pi radians. Mode. Put it in radian mode first. Quit. Now it's back where it belongs. There you go. There's an issue here. What am I doing wrong here? Cosine of 120 over 12. Jeez. Oh, I just typed it wrong. Oh, stupid. Yeah, look what I did. I typed it on the calculator wrong. Pi over 2, pi over 4, that should be a 6. Alright, stupid. Alright, there we go. If you highlight it and then hit enter, it lets it go back to you. So I'm just going to insert 6. Always a mundane detail like that. I'm always screwing up. Writing it backwards doesn't help. Okay, here you go. I may have to change the mode again. We'll see. Square root of 2 plus square root of 6. What it is. Not what I typed like a dope. 0.925. Alright. Here it is, cosine. Alright, just above it. Let me just scoop that up. The cosine of pi over 12, 0.965. Square root of 2 plus square root of 6 divided by 4 is 0.965. It's the same answer. All right. If you get a different answer, it could mean that you're just in the wrong mode. So switch between pi radians and degrees. Okay. Blue. I erase this habit. We're getting near the end here. All right, the last 3 problems, 33, 34, and 35, are non-right triangle trigonometry. So let me see if I can confine myself to one board here. All right, in the case of 33, it says find the measure of x, which is an angle. You have a picture that looks like this. This is x. And you have dimensions of 10 here and 5 here, and then this is labeled 98. Right. Now remember, if you're trying to decide between laws of sines and laws of cosines, right? law of sine would be if you're given these situations. Right? If you're given an angle, a side, and an angle, an angle, an angle, and a side, in that order, and then as politeness, a side, and an angle. In which case, you're going to use a trig ratio like this with some derivative, a proportions equation. All right, if on the other hand, you're looking to use law of cosines, these are more complicated, but they're derived from the Pythagorean Theorem. This is if you are given the other two situations, a side, an angle, and a side in that orientation, or a side, a side, a side. So SAS or S, S or SA. Sorry, I'm being goofy now. All right. Anyhow, I gave you the formulas to choose from. Let's just confirm that this is appropriate. All right. What's given? We have a side, an angle here, okay, this angle, and then I have a second side. So what do I have? I have a side, and an angle, reading it like that, as opposed to reading it backwards. So it is appropriate to use this. All right. How you would figure out what is A, what is B, what have you. It doesn't matter, just try to be consistent about what is across from what, right? If in other words, if instead of calling this X for the moment, I call this A, right? What is across from A, the angle? A, the dimension, the length. If this is B, right, then this side would be the B dimension. If this is then C, then this across from this would be the C dimension here. And just to tweak my formulas just ever so slightly, what I would do is, yeah, I'm definitely going to use some proportion equation like this. I'm just going to change the labels. All right, I'm going to go, all right, the sine, instead of calling it A or alpha, I'm going to call it X, because that's what they're calling it in the problem. And then I'm going to call A 5. All right. Then I'm going to use the C dimensions. Right? The sine of C and lowercase c, as opposed to being, because of the way I've arranged it here. And the numbers would be sine of 98, and this would be 10. Okay. All right, now as you solve this, it is cross multiplication technique. All right. So to cross multiply this way would be produce this half of the equation as a proportion equation, 5 the coefficient, the sine of 98 degrees. And to cross multiply this way would be 10 the coefficient and the sine of x, which is what we're looking for. If you want to use a inverse trig function, that's fine, but just make sure that you isolate first. So divide by 10 here, and divide by 10 here. And then this is the sine of x is equal to, you could simplify the coefficients, right? You could just write it as either 0.5 or a half the sine of 98. I guess if you're typing it on your calculator, probably 0.5 would be the easiest thing. Then use the inverse sine function. So the inverse of 0.5 times the sine of 98 would give you what the x angle is. I'm going to change it back to degree mode because I know I messed with it. So let me just clear this. Okay, quit. And now type this. The inverse sine of 0.5 times the sine of 98 embedded in it. All right, so something typed like that. Hit enter, and then you get 29 degrees and a little bit extra. So if it was asking to round to the nearest tenth, x, if it's equal to 29.67 rounded to the 10th place is where the 6 is, so you'd say it's about 29.7 degrees. Which is choice C. Okay. I got 2 more. Oh, blue. I keep saying that. I probably keep picking up more blue, that's why. Stinks when you have that many choices sometimes. Let me put that here. Okay. Problem 34. In the case of 34, I already told you to use the law of cosines, but how would you know if it wasn't stated? Right? If you have dimensions of 115, 125, and 100, and nothing else, and they're asking you to solve for A, right? But they've given you a side, and a side length, then that's appropriate to use the law of cosines. Now, if they happen to be calling this A here, just take the time to figure out what is across from the A, the things that the corresponding letter in lowercase, essentially. Across from A angle would be A side dimension. That would mean, right, that as far as the other dimensions are concerned, I'm just going to go in sort of counterclockwise order here. If this is B, right, then that would be B for that dimension, and that would force this to be C, and that would be C as 100, which kind of makes sense, right? C note, right? Cento, right? And the appropriate incarnation of the law of cosine would be one that involves angle A. Right? So the one that would work most appropriately is this one. A squared is equal to B squared plus C squared minus 2BC, the cosine of A. You're going to basically use an inverse trig function again, but rearrange the parts first. In fact, don't even bother substituting the values until after you've gotten it rigged up first. All right. How would you know that you have to choose this particular one? This is the one that's labeled A, right? And since you're given sides, all right, look what you're going to be using. 125, you got to put things in the appropriate places is really the bottom line. But let me rearrange a little bit. If I took this, and this is long and complicated, but if I took this term, this whole thing, and it is one term, notice there's a minus here, and just plopped it on the opposite side, right, then it would be positive over here, and you would have this written like so. If, because I'm trying to isolate this, right, I did two things in once. I'm trying to get this away from all this stuff, all the terms, and there would technically be two other terms, and I'm also trying to avoid there being a negative there. So I put it on the opposite side. I am going to do the same thing with A. I'm going to take this term and just move it over here. If it's positive here, then it would be negative over here. The last thing is I'm going to move the coefficients. What are the coefficients of cosine? 2B and C simultaneously. You'd have this. And now again, if I'm trying to solve for the angle A, then A should have to be the inverse cosine of all of this gobbledygook. Just plug in the numbers in the appropriate places. A is across from the angle that we're looking for. So 125 has got to be here. And C should be here, and also here. And 115 should be here, and also here. You can type all of this into your calculator, but if you do, just make sure that you incorporate the appropriate parentheses because it might get a little screwed up. In other words, there should be a parentheses around that, and around that, around that, all right, and around these two. All right. 115, 100, 125, 100. And then this is its own top. So that's a lot of parentheses, but I would definitely make sure that the top is all clear. You could figure out what these things are individually and just make one top if you want. But it would work, all right, if you typed it. Anyhow, this is what the angle would be, rounded to the 10th place. It would be about equal to 70.7 degrees. Finally, the last thing is Heron's formula. Using the same dimensions, which is terrible of me, but make extra credit next time. Yes, I put a note here to myself. Yes, make it an extra credit. Not this time. Heron's formula is a way of calculating the area using the semi-perimeter, which is the half of a perimeter, which is an S. So it's two things that you need to know. You need to know what S is, understand that it's half of a perimeter, which means that it's the side dimensions divided by 2, all right? And then the actual formula, Heron of Alexandria, is equal to this. The area is equal to the square root of that semi-perimeter, and then the quantity of that minus A, that quantity minus B, and that quantity minus C, all under this. Now, the only thing that you really have to do, because you already know what A, B, C are, right? A is 125, right? B is 115, and C is 100, is add them together and see what you get. It turns out that 115 plus 125 plus 100 is a big number. All right, 2, 15, 10, 4, 340. All right, I'm about to divide by 2. Okay. Let's see. So clear 125 plus 115 plus 100. 340 divided by 2. 170. Okay. So you're going to squeak 170 in here, 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 and here. And I would use again parentheses, to make sure that you get it correct. So I'm going to add to that now. The square root of 170 let's see, times the quantity 170 minus 125 times the quantity 170 minus 115 times the quantity 170 minus 100. Alright, as I've typed it, semi-perimeter all the way across here, and put it like so, all underneath the square root, and you get that 5,424. Okay, if this is an area, I didn't specify round, I did put round to the nearest tenth. So if it's 5,427.01, the 10th place is where 0 is. This is about 5,427 units, whatever the units are, squared. Okay, it wasn't a dope, I just had to write this. So I forgot to write for something here. Bear with me. that's it. That is a summary of basically all of the material from the spring 2020 semester. Yay! It's over. Anyhow, I wish I could say goodbye to all of you in person, honestly. But anyhow, I'm gonna enter the credit for the final exam now. All right, and in maybe a day or two, you'll see that I'll have it updated, the letter grade in WebAdvisor. All right, but you'll know what your grade is ahead of time, you know, or at least approximately, in the Canvas gradebook. Okay, thank you for your patience. It's three and a half hours. All right, but we're done. All right, and stay safe. Okay, perhaps I'll see you. All right, take care.